So Chapter 2 talks about how we can model distributions of data and also where we can find a piece of data within that distribution. Here are your objectives. I'll talk more about each objective in the following slides. I guess I can't talk too much because YouTube wouldn't take this, so I'm cutting it short. You'll notice that there might be some weird clips moving forward because I had to cut some slides out. So here we have the idea of percentile, and percentile is basically looking at the percentage of the observations that are less than that. Key issues are you recognize that percentile does not mean the percent right. It is their location in a distribution, and you're always going to be talking with percentiles or z-scores or any of those. You're always talking about how much is less than that particular data item. So here we have Jenny. She's in the 84th percentile because she has an 86, so we're going to go ahead and look at all of the data that's below the 86, and there's 21 below 86. So she's at a cut point, and we're looking at the percent of stuff that's below it. So 21 out of the 25 total in the class were below 86, so that puts her at the 84th percentile. So you might want to stop me and do this yourself, but the question is, what is your percentile if you were at a 10.7 time? And most of the time it's better to be up here, but in this particular case it means you're slower, and it's actually not a good thing. So you want to actually be down here. So 10.7, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 out of the 18 out of the 20 18 out of the 20 total data points were below 10.7, so we're talking about, let's see, 8 times 5, a 95. She's in the 95th percentile, right? 8 times 5, 25, yep. She's so let's make sure first we get the straight between frequency, relative frequency, and cumulative relative frequency. So first we have frequency. How often a data, in this particular case, they've categorized things by age, and from 40-44 there were 2 presidents that were that age. And so a frequency graph can be a dot plot or a histogram. And so we would go ahead and put 2, and then we'd put 7, and all that kind of stuff. Then we get to relative frequency, and we would take the percent of the total that hit within that category, and it would still look like a dot plot or a histogram, but instead of raw numbers over here, we're going to talk about percents. And relative frequency, once again, is always a good idea when there is. So the cumulative relative frequency is then just the percent version of adding all of the things that happened to before it. So here we are at a frequency of 2. It was 2 out of 44. By the time we look at all of the 40 to 49 together, that's 9 presidents. So basically, here we would have a total of 9 dots right here, if we could. And here we'd have a total of 2 dots right there. And by the time we hit the top of this graph, we're going to have all 44 presidents. Okay? But what a cumulative relative frequency graph does is it changes that to percents. So at the very top of a cumulative relative frequency graph, we're going to have 100% of the data, and at here we would have a total of this looks pretty wild, and we'll be doing a lot of this, but basically we're going to take the an individual's location, and we're going to go ahead and subtract their location from the mean, divide by the standard deviation, and that's going to be their z-score. And their z-score tells you where it fits in the normalized curve. So here, x minus the mean divided by the standard deviation. She had an 86, the mean was an 80. We divide by 6.07, and she's at a 0.99. So if we were going to go ahead and look at her location, here's our 80. Here's our 80, 6.07. Here's a standard deviation of 1. Our friend Jenny here is just below that. She's somewhere just below, just below that. I can't even draw it properly. She's really close to a standard deviation of 1. We're going to talk about transforming data a little bit. We're going to do this a couple times in a couple of different activities in class. But this comes from the idea of a set of students who were guessed to ask how long their room was in meters, and they came from Australia, which Australia and the United States were the only two countries that didn't use the metric system. So when the metric system was introduced to Australia, there was a bit of a difference between what was correct and what wasn't. So looking at this distribution, you could take this as an opportunity to kind of stop the video and remind yourself what each of these things mean, the minimum right here and the maximum right here, and you could go ahead and locate the Q1 and the Q3 and the median and all that stuff, figure out IQR. Remind yourself particularly, and here's the standard deviation. So the actual length of the room was 13 meters, and so if we were going to come up with a way of measuring their error factor, we could say that we could take someone's guess and subtract 13 from it, and that would give us their error, how much they erred by. So we can then go ahead and look at, here's our original data, and then we're going to look at what happens when we subtract everything. Think for a moment, how is that going to affect the distribution? Because we're going to so we'll notice that when we subtract 13 from each of the guesses, the mean goes down by 13. Not a big surprise. When we subtract 13 from each of the guesses, the minimum goes down 13, the Q1 goes down 13, the median, etc., all those. The IQR doesn't change. The difference between the Q3 and the Q1, even though the numbers are different, the distance between them is 6, and the range doesn't change either. The minimum and the maximum changes, but the number of data points between doesn't change. Standard deviation. We will summarize this in class again also when we look at our own data stuff, but adding the same number or subtracting the same number from an observation, whatever number is subtracted, that's going to drop everything. It's going to drop the mean, it's going to drop the median, it's going to drop the quartiles, it's going to drop the percentiles, that number. So in this particular case, everything dropped by 13. The shape of the distribution doesn't change, and the measures of spread don't change. So adding or subtracting, it changes the centers and all of your 5-number summary. But your spread doesn't change and your shape. So since these kids didn't know their meters very well, it's probably easier to explain how far they were off in terms of feet. So here is their error data in meters. And then if we wanted that error data in feet, we would multiply by 3.28. And of course, if we already had it in feet, we could divide by 3.28. But we're going to take the error data and multiply by 3.28 because there's roughly 3.28 feet in a meter. Now, we'll notice what happens. Obviously, it's more spread out, so there is an effect in our IQR and our range. We'll notice that, wait, the shape is the same. So the shape still stays the same. And then what's happening to each of the each of the demarcation points, for lack of better term, in the 5-number summary is 3.28 times bigger, and the standard deviation is 3.28 times bigger. So multiplying or dividing by some number, in this case 3.28, the measures of center, mean, mode, median, all the location parts are affected by that multiplication factor or that division factor. The measures of spread are affected, but it's going to be by the absolute value of b, by the positive version of b if we were happen to be multiplying or dividing by a negative number. But you notice it does not change the shape of the distribution. It was more spread out, but it's the same. Here are your summary from the section. Check to see if there's anything you need to ask questions about tomorrow. We'll be doing a lot of work with these things.